The Classified Cataclysm. In 1966, a book was published that made some extraordinary claims about Earth's past and future. Titled The Adam and Eve Story, it was written by Dr. Chan Thomas, a former engineer for McDonnell Douglas. Shortly after its release, the book was classified by the CIA and essentially disappeared from public view for decades. It wasn't until 2013 that a partially declassified version of the book was released, with significant portions still redacted. This, of course, only increased interest in its contents. What could this book contain that would make the CIA want to keep it hidden for nearly 50 years? The Adam and Eve Story puts forth a radical theory that Earth periodically experiences catastrophic pole shifts that wipe out most of humanity and reset civilization. According to Thomas, these cataclysms occur in cycles of several thousand years. He claimed we were nearing the end of the current cycle and that another worldwide disaster was imminent. Now, this may sound like the plot of a Hollywood disaster movie. But Thomas presented his ideas as scientific fact, based on geological evidence and his interpretation of ancient texts and myths from around the world. He argued that there have been at least 5 previous advanced civilizations on Earth, each destroyed by a rapid shifting of the planet's crust. Let's look at how Thomas described this cataclysmic process. The entire crust of the Earth would shift in a matter of hours, taking with it oceans, mountains, and entire continents. The movement would be accompanied by earthquakes, volcanic eruptions, and colossal tidal waves. In a single day, the destruction would be nearly total. Only a fraction of the human population would survive, thrown back to a primitive existence. Thomas claimed the trigger for these events was a disruption in Earth's magnetic field, which would cause a thin layer of molten rock beneath the crust to temporarily liquefy. This would allow the entire crust to slide around freely, with the weight of polar ice caps pulling it into a new orientation. As the crust shifted, the oceans would continue their eastward rotation at over 1,000 miles per hour, creating massive tsunamis that would sweep across entire continents. Areas that were once temperate would suddenly find themselves at the poles, flash freezing in a matter of hours. Meanwhile, the former polar regions would move to the equator and rapidly thaw. According to Thomas, the last such cataclysm occurred around 6,500 years ago and was the source of global flood myths found in cultures worldwide. Before dismissing this idea as absurd, consider how it aligns with some scientific findings and ancient traditions. Geologists have found evidence of rapid, dramatic climate shifts in Earth's past, including periods when tropical regions became frigid in a matter of decades. Many cultures around the world have myths of great floods or other catastrophes that destroyed previous civilizations. There are underwater structures and formations that some believe are evidence of sunken ancient cities. Certain archaeological sites show signs of sudden, cataclysmic destruction. Earth's magnetic poles are known to reverse periodically, and some scientists believe this could happen again in the near future. While the specific mechanism Thomas proposed is not accepted by mainstream science, the idea of periodic global catastrophes reshaping the planet is not as far-fetched as it might initially seem. In fact, we know with certainty that Earth has undergone multiple mass extinction events in its history. The most famous of these, 66 million years ago, wiped out the dinosaurs and 75% of plant and animal species on the planet. More recently, at the end of the last ice age around 12,000 years ago, there is evidence of rapid sea level rise, climate change, and widespread extinctions of large mammals. Some researchers believe this may have been triggered by a comet impact or other cosmic event. He predicted another shift would happen around the year 2000, giving humanity only a few decades to prepare when his book was published in 1966. Of course, the year 2000 came and went without any such world-ending catastrophe. So was Thomas simply mistaken? Or could his timing just have been off? To evaluate his claims, we need to look at the evidence he presented and how it holds up to scientific scrutiny. But first, let's step back and consider, why would the CIA classify a book making such seemingly outlandish claims? What made Thomas' ideas so dangerous or sensitive? Some have speculated that the CIA knew Thomas was onto something and wanted to suppress the information to prevent widespread panic. Others suggest it may have had more to do with Thomas' background in aerospace engineering and his claims about anti-gravity technology. The CIA has never officially commented on the matter. What we do know is that the partially declassified version released in 2013 is only about 57 pages long, reportedly less than a quarter of the original manuscript's length. So what was in those missing pages? Did they contain information even more explosive than what we've seen? Or was the classification simply a case of overabundant caution during the Cold War era? These are questions that continue to intrigue researchers and fuel speculation to this day, that help popularize the concept of catastrophic pole shifts in alternative research circles. In the coming chapters, we'll take a deeper look at the evidence for and against some of Thomas' claims. We'll examine geological and archaeological findings that some interpret as signs of past global catastrophes. And we'll explore how these concepts tie into myths and legends from around the world. But first, let's zoom out and consider the bigger picture of how Earth changes over time. Chapter 1: A Dynamic Planet. To understand the plausibility of sudden, catastrophic changes to Earth's geography, we need to first recognize just how dynamic our planet truly is on geological timescales. We tend to think of the continents as fixed and immovable. The world maps we grew up with show familiar outlines that have remained largely unchanged throughout recorded history. But when we zoom out to a perspective of millions of years, we see that the face of our planet is in constant flux. The theory of plate tectonics, now universally accepted by geologists, tells us that Earth's crust is divided into massive plates that float on top of the semi-molten mantle below. These plates are in constant motion, driven by convection currents in the mantle. They collide, separate, and slide past each other at rates of a few centimeters per year. This may seem imperceptibly slow on a human timescale. But over millions of years, it leads to dramatic changes. Continents drift apart to form new oceans, or collide to form mountain ranges. What was once a coastline can become inland, and vice versa. Let's look at how Earth's geography has changed over the past 250 million years. Around 250 million years ago, all of Earth's landmasses were joined together in a supercontinent called Pangaea. This massive landmass began to break apart around 200 million years ago. By 140 million years ago, it had separated into two large continents, Laurasia in the north and Gondwana in the south. These continents continued to fragment and drift. India separated from Africa and began its long journey northward, eventually colliding with Asia to form the Himalayas. South America and Africa pulled apart, opening up the Atlantic Ocean between them. North America separated from Europe. By 60 million years ago, the continents were nearing their current positions, though still with some significant differences. For instance, Australia was still connected to Antarctica at this point. It's only in the past 30 million years that it separated and drifted northward to its present location. Even in more recent geological history, we see significant changes. During the last ice age, which peaked around 20,000 years ago, so much water was locked up in ice sheets that sea levels were about 120 meters, nearly 400 feet, lower than today. This exposed vast areas of continental shelf, significantly altering coastlines worldwide. For instance, the British Isles were connected to mainland Europe. Indonesia was joined to Southeast Asia as part of a vast landmass geologists call Sunderland. And a land bridge connected Siberia to Alaska, allowing humans to migrate from Asia to North America. As the ice sheets melted over thousands of years, these low-lying areas were gradually flooded. Some researchers have suggested that memories of this flooding may be the source of flood myths found in many cultures. The key point here is that Earth's geography is far from static. While the processes of plate tectonics typically operate too slowly for us to perceive, they can lead to massive changes over geological timescales. But what about more rapid changes? Could Earth's geography be altered dramatically in a matter of days or even hours, as Chan Thomas claimed? To answer that, we need to look at some of the more extreme geological events in Earth's history. Chapter 2: Catastrophes of the Past. While gradual change is the norm in geology, Earth's history is punctuated by episodes of rapid, sometimes catastrophic change. Let's examine some of these events and consider their implications. The Chicxulub impact, about 66 million years ago, an asteroid or comet at least 10 kilometers in diameter slammed into what is now the Yucatan Peninsula in Mexico. The impact released energy equivalent to 10 billion Hiroshima bombs, sending a cloud of superheated rock and dust into the atmosphere. The immediate effects were devastating: massive tsunamis, widespread fires, and a blast of thermal radiation that would have been lethal for thousands of miles. But it was the longer-term climate effects that led to a mass extinction. Dust and aerosols in the atmosphere blocked sunlight for years, leading to a prolonged global winter. This climate shock wiped out about 75% of plant and animal species on Earth, including most dinosaurs. The Deccan Traps eruptions, around the same time as the Chicxulub impact, a series of massive volcanic eruptions was underway in what is now India. Over a period of about 1 million years, these eruptions covered an area the size of France with lava over 2 kilometers thick in places. They released enormous amounts of carbon dioxide and other gases, causing long-term climate change that contributed to the mass extinction. The Great Oxygenation Event. This was a more gradual but no less profound change that occurred about 2.4 billion years ago. The evolution of photosynthetic bacteria led to a buildup of oxygen in Earth's atmosphere. While oxygen is essential for most life today, it was toxic to many of the anaerobic organisms that dominated early Earth. This event led to a mass extinction of anaerobic life and paved the way for the evolution of more complex organisms. The Younger Dryas impact hypothesis. Moving to more recent times, some researchers have proposed that an extraterrestrial impact, or series of impacts, may have occurred around 12,800 years ago, at the start of a period of abrupt cooling called the Younger Dryas. Proponents of this hypothesis point to geological evidence including a layer of microscopic diamonds, magnetic spherules, and elevated levels of platinum and iridium found in sediments from this time. They argue that an impact, or impacts, could have melted parts of the North American ice sheet, disrupting ocean circulation patterns and triggering the cooling event. This hypothesis remains controversial, with many scientists arguing that the evidence can be explained by other mechanisms. If true, it would represent a catastrophic event occurring within human prehistory, potentially affecting early human cultures. The Bronze Age collapse. Around 1200 BCE, multiple advanced civilizations around the Mediterranean and Near East experienced a sudden and dramatic collapse. Within a span of just 40 to 50 years, great cities were destroyed, trade networks collapsed, and entire writing systems were lost. While not a geological catastrophe per se, this event demonstrates how seemingly stable civilizations can experience rapid, systemic collapse. The causes are still debated, but likely involved a combination of factors including climate change, invasions, and social upheaval. These examples show that Earth has experienced sudden, dramatic changes in the past, some of which have had profound effects on life and human societies. The question remains, is such a drastic shift of Earth's crust physically possible? To answer that, we need to delve deeper into the science of Earth's structure and magnetic field. Chapter 3: Earth's Hidden Layers. To understand the plausibility of crustal displacement theories, we first need to understand the structure of Earth's interior. While we can't directly observe most of Earth's layers, scientists have built up a detailed picture through various lines of evidence including seismic waves, magnetic field measurements, and the study of meteorites. Earth's interior is divided into several distinct layers. The crust. This is the thin outer layer we live on, ranging from about 5 to 70 kilometers thick. The crust is solid and relatively rigid, made up mostly of lighter elements like silicon and aluminum. The mantle. Beneath the crust lies the mantle, which extends to a depth of about 2,900 kilometers. While mostly solid, the mantle can flow like a very thick liquid over long time periods. This slow flow drives plate tectonic movements. The outer core. Below the mantle is the outer core, a layer of liquid iron and nickel about 2,200 kilometers thick. The movement of this conductive fluid generates Earth's magnetic field through a process called the geodynamo. The inner core. At Earth's center is the inner core, a solid ball of iron and nickel about 1,220 kilometers in radius. Despite the intense heat, it remains solid due to the enormous pressure at the center of the planet. Now, Chan Thomas's theory relied on the idea that there's a thin layer of molten rock just below the crust that could act as a lubricant, allowing the entire crust to slide around freely if perturbed. He claimed this layer becomes liquid when Earth's magnetic field is disrupted. There is a layer in the upper mantle called the asthenosphere where rock is close to its melting point and can flow more easily than the layers above and below. This layer plays a crucial role in plate tectonics, allowing the rigid plates of the lithosphere, the crust and uppermost mantle, to move around. But even this more ductile layer doesn't allow for the kind of rapid, wholesale crustal movement Thomas described. The processes of plate tectonics operate on timescales of millions of years, not hours or days. What about Thomas's claims regarding Earth's magnetic field? While he was correct that the field can change and even reverse polarity, the process doesn't work quite the way he described. Let's take a closer look at Earth's magnetic field and how it changes over time. Chapter 4: The Wandering Poles. Earth's magnetic field is generated by the movement of molten iron in the outer core, a process called the geodynamo. This field extends out into space, shielding our planet from harmful solar radiation and cosmic rays. It's what makes compasses work and helps some animals navigate. But Earth's magnetic field isn't static. It changes over time in both strength and direction. The magnetic poles are constantly moving, and occasionally, the field reverses completely, magnetic north becomes south and vice versa. These reversals have happened hundreds of times over Earth's history. We know this from the magnetic alignment of minerals in ancient rocks. When certain rocks form, magnetic minerals within them align with Earth's magnetic field like tiny compass needles. This alignment is preserved as the rocks solidify, providing a record of the field's orientation at that time. By studying rocks of different ages, geologists have built up a timeline of magnetic field reversals going back hundreds of millions of years. They found that reversals happen at irregular intervals, with some periods of stability lasting tens of millions of years, and others seeing multiple reversals within 1 million years. The last full reversal, called the Brunches-Maruyama reversal, occurred about 780,000 years ago. Given that the average time between reversals is around 300,000 years, we're statistically overdue for another one. In fact, Earth's magnetic field has been weakening at an unusually rapid rate in recent years. The field has lost about 9% of its strength over the past 200 years. The North Magnetic Pole has also been moving faster, from about 10 kilometers per year in the early 20th century to about 50 kilometers per year recently. Some scientists interpret these changes as signs that we may be entering a period of reversal. During a reversal, the magnetic field doesn't simply vanish. It becomes more complex, with multiple north and south poles emerging in different locations before it settles into the reversed configuration. The field also weakens significantly during this process, potentially dropping to about 10% of its normal strength. A weakened magnetic field during a reversal could have significant impacts. More solar radiation would reach Earth's surface, potentially affecting climate and increasing cancer rates. It could also disrupt power grids and satellite communications. However, there's no evidence in the fossil record of mass extinctions coinciding with past geomagnetic reversals. This suggests that life on Earth can adapt to these changes, even if they might pose challenges for our technology-dependent civilization. It's also worth noting that magnetic pole shifts are distinct from geographic pole shifts. The geographic poles are the points where Earth's axis of rotation intersects its surface. While these can shift slightly due to changes in mass distribution, like the melting of ice sheets, they don't undergo the kind of dramatic shifts that Chan Thomas described. So, while Earth's magnetic field does indeed change over time, the process doesn't provide a mechanism for the kind of rapid crustal displacement Thomas proposed. But if not through magnetic effects, could other forces cause sudden shifts in Earth's crust? Let's explore some other theories. Chapter 5: Alternative Theories of Earth Changes. While mainstream geology doesn't support the idea of rapid crustal displacement, other researchers have proposed alternative mechanisms for sudden Earth changes. Let's examine a few of these theories. Earth crust displacement theory. This idea was popularized by Charles Hapgood in his 1958 book Earth's Shifting Crust. Hapgood proposed that the weight of ice accumulating at the poles during ice ages could cause the entire crust to slide over the mantle, repositioning continents relative to the poles. Hapgood's theory gained some attention when Albert Einstein wrote the foreword to his book. Expanding Earth theory. Some researchers have proposed that the Earth is slowly expanding over time, causing continents to move apart. They point to the fact that the coastlines of continents seem to fit together better on a smaller globe. Cosmic impacts. While we discuss the potential Younger Dryas impact, some researchers propose that Earth has been subjected to multiple, catastrophic cosmic impacts throughout its history. These could potentially cause rapid changes to Earth's geography and climate. Catastrophic pole shift hypothesis. This idea, popularized by author Graham Hancock among others, suggests that the geographic poles have shifted rapidly in the past due to changes in mass distribution on Earth's surface. Galactic cycles. Some alternative researchers propose that as our solar system moves through different regions of the galaxy, it encounters varying levels of cosmic radiation or gravitational influences that could trigger Earth changes. Solar micronova theory. This recent theory suggests that the Sun periodically releases an enormous burst of energy and matter, far beyond the scale of normal solar flares. Proponents claim this could cause rapid melting of ice sheets, floods, and other cataclysmic effects on Earth. Now, let's turn our attention to one of the most enduring mysteries in alternative history, the legend of Atlantis and other lost continents. Chapter 6: Atlantis and Lost Continents. The story of Atlantis, a highly advanced civilization suddenly swallowed by the sea, has captivated imaginations for thousands of years. First described by the Greek philosopher Plato around 360 BCE, Atlantis has been the subject of countless books, movies, and expeditions. According to Plato, Atlantis was a powerful maritime empire located beyond the Pillars of Hercules, the Strait of Gibraltar. He described it as larger than Libya and Asia combined, with a sophisticated system of canals, a grand capital city, and formidable military might. Plato claimed that Atlantis was destroyed by earthquakes and floods in a single day and night, sinking beneath the waves about 9,000 years before his time. For centuries, people have searched for evidence of Atlantis. Proposed locations have ranged from the Mediterranean to the Atlantic, and even as far as Antarctica. Many scholars today believe that Plato invented Atlantis as an allegory to illustrate his political ideas. Others suggest he may have been inspired by real events, such as the destruction of Minoan civilization on Crete by a massive volcanic eruption on the nearby island of Thera around 1600 BCE. But Atlantis isn't the only lost continent in legend and alternative history. Let's look at a few others. Lemuria. This hypothetical lost continent was proposed in the 19th century to explain the distribution of lemur fossils found in Madagascar and India, but not in Africa or the Middle East. The idea was that a continent once bridged the Indian Ocean, allowing lemurs to spread, and then sank beneath the waves. While the concept of Lemuria was briefly considered by some scientists, it was abandoned as the theory of plate tectonics developed. We now know that India was once connected to Madagascar as part of the supercontinent Gondwana, explaining the lemur fossil distribution without need for a lost continent. Mu, this legendary lost continent, sometimes conflated with Lemuria, was popularized by Augustus Le Plongeon and James Churchward in the late 19th and early 20th centuries. They claimed Mu was located in the Pacific Ocean and was the origin of many ancient civilizations. There's no geological evidence for a sunken continent in the Pacific. The Pacific seafloor is composed of oceanic crust, which is denser than continental crust and doesn't support the existence of a lost landmass like Mu. Zealandia. Unlike the others, Zealandia is a real, scientifically recognized continent, though mostly submerged. It's a nearly complete, mostly submerged continental fragment that broke away from Australia about 80 million years ago and includes New Zealand and New Caledonia. While not a lost civilization, Zealandia shows that significant landmasses can indeed be hidden beneath the waves. It's estimated to have been mostly submerged for the past 23 million years. The enduring appeal of lost continent myths likely stems from a combination of factors. They offer explanations for the seemingly sudden appearance of advanced civilizations in the archaeological record. They provide a canvas for imagining utopian societies free from the flaws of known history. And they resonate with a sense that our known world might not be all there is, that profound mysteries could still be waiting to be uncovered. While the specific claims about Atlantis, Lemuria, and Mu are not supported by evidence, the ideas they've inspired have led to real archaeological discoveries and a deeper understanding of ancient cultures. They remind us that human civilization has a long and often mysterious history, with many chapters still waiting to be fully understood. Now, let's explore how some of these ideas about lost civilizations and Earth changes connect to myths and legends from around the world. Chapter 7: Global Myths and Legends. Myths of great floods, lost golden ages, and world-destroying cataclysms are found in cultures around the globe. While the specific details vary, the common themes are striking. Let's explore some of these stories and consider what they might tell us about human history and the human psyche. Flood myths, perhaps the most widespread category of cataclysm myths, are stories of great floods. The biblical story of Noah's Ark is probably the best known in Western culture, but similar tales are found worldwide. In Mesopotamian mythology, the Epic of Gilgamesh describes a great flood sent by the gods to destroy humanity, with only the hero Utnapishtim and his family surviving in a great boat. Greek mythology tells of a flood in the time of Deucalion, from which he and his wife Pyrrha repopulate the world by throwing stones that become people. In Hindu tradition, Mana is warned of a coming flood by a fish, an avatar of Vishnu. He builds a boat and ties it to the fish, which guides him to safety. Mayan legend speaks of a great flood called Hunyao that destroyed the world. Chinese folklore includes the tale of Gun Yu, who spent decades building canals and dams to control great floods. Many researchers have suggested these flood myths might preserve memories of real events, such as the rapid sea level rise at the end of the last ice age. Others see them as metaphors for psychological or spiritual themes. Golden Age myths. Many cultures have stories of a past golden age when humans lived in harmony with nature and each other. This paradise is often lost due to some transgression or cataclysm. In Greek mythology, the Golden Age was the first of 5 ages of man, an era of peace and plenty under the rule of Cronus. The Garden of Eden story in Abrahamic religions describes a paradise from which humans were exiled. In Hinduism, the Satya Yuga or Krita Yuga was a golden age of virtue and spiritual purity. Taoist texts speak of a perfect age in remote antiquity when humans lived in harmony with the Tao. These myths might reflect a universal human longing for a simpler, more harmonious existence. Some researchers have also suggested they might preserve dim memories of the hunter-gatherer lifestyle before the challenges of agricultural civilization. Cyclical time and world ages. Many ancient cultures conceived of time as cyclical rather than linear, with recurring ages or eras. In Hinduism, the 4 yugas, Satya, Treta, Dvapara, and Kali, repeat in a cycle, with each cycle, Mahayuga, lasting 4.32 million years. Mesoamerican cultures like the Maya and Aztecs had complex cyclical calendars, with cycles within cycles culminating in great world ages. In Norse mythology, the current world will end in the cataclysm of Ragnarok, only to be reborn and begin anew. These cyclical worldviews contrast with the linear time concept dominant in modern Western thought. They suggest a view of history as a recurring pattern rather than a straight line of progress. Sunken lands. Stories of lands lost beneath the waves are found in many coastal cultures. Welsh folklore tells of Cantarag Gwaelod, a fertile lowland supposedly flooded when a drunken gatekeeper failed to close the sea walls. Japanese legend speaks of Mu, a Pacific continent that sank beneath the waves, likely influencing later Western ideas about Mu. Indigenous Australian traditions include stories of lands now beneath the sea, some of which align with areas known to have been above water during the last ice age. Some of these legends may preserve memories of real coastline changes due to sea level rise. Others might reflect universal human themes of loss and the capriciousness of nature. The prevalence of these myths raises intriguing questions. Do they reflect some common experience in human prehistory? Are they independent inventions addressing universal human concerns? Or have they spread through cultural diffusion? This brings us to an important question: why are we so drawn to these ideas of worldwide catastrophe? To answer that, we need to look at the role of cataclysm in human culture and psychology. Chapter 8: Catastrophe in Human Culture. The idea of world-ending catastrophe is deeply ingrained in human culture. From ancient myths to modern disaster movies, stories of cataclysmic events have captivated our imagination for millennia. But why are we so fascinated by these scenarios? One reason might be our evolutionary history. For most of human existence, we lived in small groups constantly under threat from predators, rival groups, and natural disasters. A tendency to imagine and prepare for worst-case scenarios could have been a survival advantage. Another factor is our pattern-seeking nature. Humans are adept at recognizing patterns. It's a skill that served us well throughout our evolution. But this ability can sometimes lead us to see patterns where none exist, or to oversimplify complex phenomena into more easily understood cycles or events. Catastrophe myths also serve important cultural functions. They can act as cautionary tales, encode practical knowledge about real disasters, or provide explanations for puzzling geological features or archaeological remains. Let's look at some examples of catastrophe myths from around the world. The flood myth, stories of a great flood that destroys most of humanity, are found in cultures across the globe. The most famous is probably Noah's Ark in the Judeo-Christian tradition, but similar stories appear in ancient Mesopotamian texts, Greek mythology, and the traditions of indigenous cultures from the Americas to Australia. These myths might preserve memories of real flood events at the end of the last ice age, when sea levels rose dramatically. They also often carry moral messages about divine judgment and the importance of moral behavior. Atlantis, Plato's account of an advanced civilization destroyed by a cataclysm, has captured imaginations for over 2,000 years. While most scholars view Atlantis as a philosophical allegory rather than a historical account, it has inspired countless theories and expeditions seeking to find the lost continent. The Atlantis myth touches on deep-seated human fears about the fragility of civilization and the power of nature. It also appeals to our fascination with lost knowledge and the idea that our ancestors might have been more advanced than we realize. Ragnarok, in Norse mythology, Ragnarok is a series of future events including a great battle, natural disasters, and the submersion of the world in water. Afterward, the world resurfaces, fertile and renewed, and 2 human survivors repopulate the earth. This myth reflects a cyclical view of time common in many cultures, where destruction is followed by renewal. It might also encode knowledge about real climate fluctuations experienced by Norse peoples. The Kali Yuga, Hindu tradition, speaks of cyclical ages, with our current age, the Kali Yuga, being one of moral decay that will end in destruction before a new, golden age begins. This concept of cyclical time is common in many Eastern philosophies and contrasts with the more linear view of time in Western traditions. These myths, and many others like them, show how the idea of cyclic catastrophe is deeply rooted in human culture. They often blend explanations of natural phenomena, moral teachings, and hopes for renewal or rebirth after destruction. In modern times, these ancient myths have been joined by scientific theories about mass extinctions, cosmic impacts, and climate change. While based on evidence rather than mythology, these scientific concepts often provoke similar feelings of awe, fear, and fascination. This cultural background helps explain why ideas like Chan Thomas's pole shift theory can capture public imagination, even when they contradict scientific consensus. They tap into deep-seated cultural narratives and psychological predispositions. Global catastrophes have occurred in Earth's past and could occur again. The geological record shows they are extremely rare events. The gradual processes of plate tectonics, erosion, and climate change are far more significant in shaping Earth's geography over time. Now that we've explored the cultural context of catastrophe theories, let's return to the geological evidence. What does the rock record actually tell us about Earth's past catastrophes? Chapter 9: Reading the Rock Record. Geologists often say that the rock record is like a book chronicling Earth's history. But it's a book where many pages have been torn out, others are written in a code we're still deciphering, and still others have been overwritten multiple times. Nonetheless, careful study of this record has revealed a wealth of information about Earth's past, including evidence of truly catastrophic events. Let's look at some key pieces of evidence. Impact craters. Earth's surface bears the scars of numerous cosmic impacts. While many of these have been erased by erosion or plate tectonics, we've identified about 190 impact craters worldwide. The largest confirmed crater, the Vredefort crater in South Africa, is about 2 billion years old and was originally about 300 kilometers in diameter. These craters provide tangible evidence of catastrophic events in Earth's past. The Chicxulub crater, linked to the extinction of the dinosaurs, is perhaps the most famous example of how a single impact can have global consequences. Iridium layers, the boundary between Cretaceous and Paleogene rocks worldwide, contains an unusually high concentration of iridium, an element rare on Earth's surface but more common in asteroids. This iridium anomaly was key evidence in developing the impact theory for the end Cretaceous extinction. Similar iridium-rich layers have been found at other times in the geological record, suggesting that major impacts are a recurring, if rare, phenomenon in Earth's history. Mass extinctions. The fossil record shows that there have been 5 major mass extinction events in the past 540 million years, where more than 75% of species went extinct. These events are identified by sudden changes in the types of fossils found in rocks of different ages. While impacts have been implicated in at least one of these events, the end Cretaceous extinction, others may have been caused by massive volcanic eruptions, global climate changes, or combinations of factors. Glacial deposits, rocks from many different time periods, show evidence of past ice ages. These include distinctive types of sedimentary deposits left by glacier and dropstones, large rocks dropped into fine-grained sediments as icebergs melted. These deposits show that Earth's climate has varied dramatically over time, with periods of extensive glaciation alternating with warmer periods. Magnetic reversals. As we discussed earlier, the alignment of magnetic minerals in rocks provides a record of past reversals in Earth's magnetic field. This record shows that while reversals are common in geological time, they occur over thousands of years, not suddenly. Flood basalts, enormous lava flows, covering thousands of square kilometers, provide evidence of massive volcanic eruptions in Earth's past. The Deccan Traps in India and the Siberian Traps in Russia are examples of these large igneous provinces. These eruptions released enormous amounts of greenhouse gases and other pollutants, causing long-term climate effects that have been linked to mass extinction events. Ocean anoxic events. Certain marine sedimentary rocks contain unusually high amounts of organic matter, indicating periods when the oceans were depleted of oxygen. These ocean anoxic events represent major disruptions to the global carbon cycle and were likely associated with significant climate changes and marine extinctions. This geological evidence confirms that Earth has indeed experienced catastrophic events in its past. Moreover, there's no evidence in the rock record for the kind of regular, cyclic catastrophes Thomas described. While Earth does go through cycles, like the alternation of ice ages and warm periods, these occur over much longer timescales and don't involve the wholesale rearrangement of continents. The rock record also doesn't support the idea of advanced civilizations existing millions of years ago. While absence of evidence isn't necessarily evidence of absence, it's difficult to imagine how a technological civilization could exist without leaving traces in the geological record. So if the geological evidence doesn't support Thomas's specific claims, what does it tell us about the potential for future catastrophes? Let's explore that in our next chapter. Chapter 10: Future Catastrophes, Real Risks and Preparedness. While the geological record doesn't support the idea of regular, civilization-ending catastrophes, it does show that Earth has experienced, and will likely experience again, events that could pose significant challenges to our global civilization. Let's examine some of the real risks we face and how we might prepare for them. 1. Large impacts. While large, dinosaur-killing impacts are extremely rare, occurring on timescales of tens of millions of years, smaller but still destructive impacts are more frequent. A impact similar to the 1908 Tunguska event, which flattened 2,000 square kilometers of Siberian forest, occurs every few hundred to few thousand years. To address this risk, NASA and other space agencies have programs to detect and track near-Earth objects. There are also ongoing efforts to develop technologies that could deflect an incoming asteroid or comet if one were detected on a collision course with Earth. 2. Supervolcano eruptions. Large volcanic eruptions, while not as immediately catastrophic as major impacts, could have severe global effects. An eruption of the Yellowstone supervolcano, for instance, could blanket much of North America in ash and cause global cooling due to sulfur aerosols in the atmosphere. While we can't prevent such eruptions, improved monitoring can provide warning. Long-term food storage and plans for agricultural adaptation could help mitigate the effects. 3. Solar storms. A large solar storm like the 1859 Carrington event could severely damage electrical grids and satellite systems if it occurred today. While not a geological catastrophe per se, the disruption to our technology-dependent society could be severe. Efforts are underway to make power grids more resilient to such events, and improved space weather forecasting could provide crucial warning time. 4. Climate change. While occurring over longer timescales than the events Thomas described, human-induced climate change poses significant risks including sea level rise, increased extreme weather events, and disruptions to agriculture. Addressing this challenge requires both mitigation efforts to reduce greenhouse gas emissions and adaptation strategies to cope with the changes already underway. 5. Geomagnetic reversal. As discussed earlier, we may be due for a reversal of Earth's magnetic field. While not catastrophic in the way Thomas envisioned, a significant weakening of the field during the reversal process could have impacts on satellite operations, power grids, and human health due to increased radiation exposure. Strategies to address this could include radiation shielding for satellites, resilient design for power systems, and public health measures to address increased radiation exposure. 6. Pandemics. While not a geological risk, the potential for global pandemics is a very real threat, as the recent COVID-19 pandemic has demonstrated. Factors like habitat destruction and climate change could increase the risk of new diseases emerging. Improved global health surveillance, vaccine development capabilities, and pandemic response plans are crucial for addressing this risk. These risks, while serious, are fundamentally different from the sudden, all-encompassing catastrophe Thomas described. They are challenges we can anticipate, prepare for, and, in some cases, work to prevent. Moreover, our scientific understanding of these phenomena gives us powerful tools for prediction and mitigation. We have global networks of seismometers to monitor earthquake activity, satellite systems to track hurricanes and solar storms, and sophisticated climate models to project long-term changes. This scientific approach, grounded in evidence and peer review, is our best tool for understanding and preparing for potential future catastrophes. While it may lack the dramatic appeal of cyclical cataclysm theories, it provides a solid foundation for real-world preparedness efforts. As we conclude our exploration of Earth's past and potential future catastrophes, it's worth reflecting on what we've learned and what it means for our understanding of our planet and our place in its history. Lessons from Earth's past. As we've journeyed through Earth's history and examined various catastrophe theories, several key themes have emerged. 1. Earth is dynamic. While we often think of our planet as stable and unchanging, the geological record shows a world in constant flux. Continents move, climates change, and occasionally, major catastrophes reshape the face of our planet. 2. Change happens on many timescales, from the sudden violence of an impact to the slow grind of plate tectonics. Earth processes operate across a vast range of timescales. Understanding these different rhythms is crucial for interpreting Earth's past and anticipating its future. 3. Catastrophes are real but rare. The geological record provides clear evidence of catastrophic events in Earth's past. Truly global catastrophes are extremely rare, occurring on timescales of millions of years. 4. Science provides our best understanding. While alternative theories like Chan Thomas's can be intriguing, the scientific method, based on evidence, testing, and peer review, provides our most reliable way of understanding Earth's past and predicting its future. 5. Human imagination shapes our view of the past. Our cultural backgrounds and psychological tendencies influence how we interpret evidence about Earth's history. Being aware of these influences can help us distinguish between evidence-based conclusions and appealing but unsupported narratives. 6. Preparedness matters. While we can't prevent all natural disasters, understanding the real risks we face allows us to prepare and increase our resilience as a global civilization. 7. We are part of Earth's story. As we've seen, humans are relative newcomers to Earth's long history. Yet in our short time here, we've become a geological force in our own right, capable of influencing global systems in ways both intentional and unintentional. As we face the challenges of the 21st century, from climate change to resource management and natural disaster preparedness, these lessons from Earth's past take on new relevance. Understanding our planet's history gives us crucial context for our current moment. It shows us that change is constant, that life is resilient, and that knowledge is our best tool for navigating an uncertain future. Moreover, it instills a sense of perspective. In the grand sweep of Earth's history, our civilization is but a moment. Yet we have achieved something unprecedented, the ability to understand our planet's past and to consciously shape its future. This knowledge brings with it great responsibility. As the geologist Charles Lyell once wrote, "The present is the key to the past, but it's equally true that the past is key to understanding our present and preparing for our future." By studying Earth's long history of change and catastrophe, we gain insights that can help us build a more resilient and sustainable civilization. The story of Earth is one of resilience in the face of change, of life finding a way to persist and thrive in the aftermath of even the most severe cataclysms. As inheritors of this long history, we have the opportunity and the responsibility to apply these lessons to the challenges we face today. Whether it's addressing climate change, preparing for natural disasters, or managing our planet's resources, our understanding of Earth's past can guide us towards a more sustainable and resilient future. By embracing the perspective that geology offers, one that spans billions of years and encompasses changes on a planetary scale, we can better appreciate our place in Earth's ongoing story and make wiser choices about how we inhabit our dynamic planet. As we face an uncertain future, let's carry with us the lessons of Earth's past, that change is constant, that life is resilient, and that knowledge is our most powerful tool for survival and progress. With this perspective, we can approach the challenges ahead not with fear, but with the confidence that comes from understanding our place in Earth's grand and continuing history. Thank you for joining me on this exploration of Earth's hidden history. I hope it's inspired you to look at our planet with new eyes, to question, to explore, and to consider how the lessons of the deep past might guide us towards a better future. Until next time, keep exploring, keep questioning, and remember, in the vastness of Earth's history, every one of us has a role to play in shaping its future.